My computer, when I got home from work tonight, was giving me grief. And so I was trying to get on the internet and I couldn't get on. And I got around finally to getting onto something and missed Courtney's post. And so what I decided to do so that I could say that I actually somewhat participated in a group meeting is actually post my own. So after I got done with my quiz, I figured, hey, let's do it. So I went through and did the quiz, did fairly well, got them all right. That's considered fairly well. And I figured I'd post this so that you guys can go back and take a look at it and see if this will help you. And also help those who are having some trouble in understanding some of this. It's kind of confusing sometimes. So what I'm first going to go over is some of the things that I've read through the text to be able to determine the answers to my question. So we'll first turn to page 2 of our textbook. And it says just about down below to the left of the boat at the bottom, it says the null hypothesis is a statement of the status quo or the value will typically consider to be appropriate. It says the null hypothesis expressed with a statement involving equality or the equal sign. So we know that the null hypothesis is represented as the H with the little o, with the population mean equaling whatever is in our statement that we're looking for. It's an accepted value as being true, so it's used to use the equal sign for all the HOs. In contrast to the null hypothesis, we write the alternative hypothesis, which is represented by H and little a. I call it ha, and I call the null hypothesis, even though it kind of sounds bad, I call it ho. When we make this statement, basically you have some different options. If, for example, in every hypothesis test in this class, the null hypothesis will be a statement involving equality. The alternative hypothesis can include greater than, less than, or not equal to, which is the equal sign crossed out. When we test hypotheses, we assume the null hypothesis is true. And it says when we conduct a hypothesis test, we gather evidence against the requirements that the null hypothesis is true. And if we get enough evidence that the null hypothesis is true, we reject it. And if we do not have significant evidence against the null hypothesis, we do not reject it, also known as fail to reject the null hypothesis. So we turn now to page 3, go down to step 4, second line. It says, assuming the null hypothesis is true, what is the probability that we observe a sample mean as extreme or more extreme than the values we observed? And that this probability is called the p-value. And to find the p-value, we first calculate the number of standard deviations that x is away from the assumed value of the true mean population u. This is our z-score. This is then we use the applet to determine the probability of observing a value of z that is large or larger than the value we observed. And so the formula for this is that z equals the sample mean minus the population mean over the standard deviation divided by the square root of n. And that formula is there on page 3 also. And we'll skip over here now to page 5, where it talks about the null and alternative hypothesis. It is commonly believed that the true mean body temperature in this example is 98.6. In science, a statement of such claim as this is called a hypothesis. If there is enough evidence against a hypothesis, we reject in favor of something else. The claim representing the status quo or the commonly held belief or the usual value is called the null hypothesis. And if we gather enough evidence against the null hypothesis and to determine it should be rejected, we need another hypothesis to propose it in its place, and we call this the alternative hypothesis. Down below that, it says we label the null hypothesis HO, and the 0 in the subscript represents null, baseline, default, null effect, and etc. And our alternative hypothesis, like we talked about before, or I said before, can be that it's not equal to what the claimed HO value is, or it can be greater than or less than. When it's, here's an important thing is when it's not equal to, it becomes a two-sided. When it is less than, it becomes one-sided to the left. When it becomes greater than, it becomes one-sided to the right. And the way that I kind of am going to memorize this is that if the arrow is pointing towards the U, which is less than, then the tail is to the left. If it is obviously to the direction away from the U or pointing to the right, then I'm going to use that as being a right-tailed. And I'm going to kind of go through here really quick and show you kind of on the applet. I'm going to do a little screen sharing with you. So this is the applet. So I'm going to take away these values here and say that we're using it's not equal to, and so it becomes a two-sided tail. So what we want to do is mark this side and this side. That means there's two tails. If it's less than our value, we put it to the left of that value. So even though, say we typed in we have a positive z-score of 2, let's go back, 1.283, and it's, say we want to know that's less than that, we shade everything to the left of that, and then our p-value or probability value is up there. Let me do that again, 1.28. There you go. So if we want everything, if we were doing a left tail or a less than, we would shade everything in that. If we were going to do a right tail, we would do this side here. And then back again, being the not equal to. And I'll go through that here in just a second when we do our I could give you some answers to some homework questions. And so I'll stop sharing that for a second. Okay. So let's move on here. It says we would only use less than or greater than if we had a belief in advance that the mean was less than or greater than what was expected. So if we have, and then it also goes on to say, if we have strong reason to believe that the mean is either smaller or larger, so if we're not quite sure, and it doesn't state it, then the stated value, we collect our data, then we use the not equal to in our alternate hypothesis. It says here, it is important that the null and alternative hypothesis be determined prior to collecting the data. It is not appropriate to use data from our study to choose the alternative hypothesis. You can only imagine that if I already had the data, I could actually manipulate the outcomes of the study. So you can kind of see why that's not appropriate. This is an example of using data twice, once to choose the test and again to conduct the test. says, is it okay to use data from a previously study to determine your null and alternate hypothesis, but it is improper to use of statistical procedures to use the data to define and conduct a hypothesis test. So you can use the data, but make sure you, before you get started, that you have those two things in line. Once again, here on this page 5, it says the null hypothesis will all be a statement involving equality or the equal sign. Next, we say, we assume that the null hypothesis is true and gather evidence against it. In other words, we do research or collect data to gather evidence against that hypothesis. If we are unable to reject the original hypothesis, we do not conclude that it is correct. For example, we do not know that Einstein's theory of relativity is correct. We have simply not been able to disprove it yet. So even though, it's kind of funny that even though you, in your little thing that you said, hey, you know, I'm going to reject this, it's just that you failed to reject it. Doesn't mean that it's actually not true. So basically the study starts to go over and over until you try to figure it out. And I don't know if you ever truly can, just depends at what point. I'm not quite sure. It doesn't say it in the book. Do you finally say, yeah, we got enough evidence? It says, in the same way, we never can prove a null hypothesis is true. We can only gather evidence against it. If we get enough evidence, we reject the null hypothesis. So we'll just go with that. I won't go into anything deeper than I'm not reading. It says also that on page 6, it says also the sample mean reasonably close to the assumed population mean. It is important to remember that the standard deviation of the sample is the standard deviation over the square root of n, and we used that formula in our previous lessons. We need to determine how far x is from the x bar, which is the population, or the sample mean is from the population mean. Since we know the standard deviation in this case, we can use the z-score to determine if the sample mean is far from the assumed value, and we call this the statistics. So that z-score that we're going to find, just down below it says where the z is the test statistics, x is the sample mean, u is the population mean, and the standard, and the, I call it q, I don't know, it's that little circle with the line in it, is the standard deviation, and n is the sample size. And this is based upon the results from the formula above. X, oh, that's just in their thing, x is above 6 standard deviations below the mean. So when we have a positive value for our z, that says that that's how many standard deviations from the mean it is. If it's positive, it's to the right of the 0. If it's negative, it's to the, below the mean. So sorry about that. Above the mean, below the mean, based upon being positive or negative. I've already done the applet demonstration. You can see it on page 7. I'll bring that applet up again just in case let's see. Oh. Bring the applet up here. Okay, there we go. So the two-tailed, which is not equal to, you shade these two sides. A left-tailed, you just everything to the left of the value. So if this is a negative value, it's this way. If it's a positive value, then you, like this number, then you'd go all the way across. Vice versa, if it asked, if you got that z-score and it said greater than, you shade everything this way. So, and then, so right-tailed of that value, yeah, like in this particular thing, they've dropped this score, and I found that you can highlight that and drop that down, and you can go like this, shade that area and that area. So Another thing down below here is says if your population mean is close to if the sample mean is close to the population mean, then this z-score will be small. If the z-score is small, then there will be a lot of area in the tails beyond z. In other words, the p-value will be large. So let me see if I can explain that. So it's basically if you take and say your population mean is 145 and your sample mean is 145 and your population mean is 147. So 145 minus 147 is like a -2, and then when you divide that by whatever, then you're going to come up with the z-score is going to be a small z-score if those are really close together. And obviously if you have when you check that and you say you have your sample mean is like 156 and your population mean is like 190, obviously you're going to get a larger z-score. And so when we talk about z-scores, we're talking about how far away from the mean. So if it's a small z-score, we're going to be having a lot of area to the left and to the right of that. They got an example here. I can't read that number. So let's say that we chose that it was a good small number. Let's go 0.385 standard deviations. Okay, so that probability value, see, goes way up. Whereas if you're out far away from there, say like 4.560, that number gets way high. And then in your reading, you'll also see that on page 6 at the very bottom, it talks about what to do with this and how to put it in scientific notation. And it also continues on page 7. So I'll go back to explaining the next step, which is the level of the significance of the call it the level of significance, which is also known as alpha. So let me close this down here. There we go. Screen share to them. Okay. So on page 8, this says, how do we decide if the p-value is small enough to reject the null hypothesis? And it talks about in the previous lessons of 0.05 being that number. And also, if you read down further, they've also allow it as 0.1 or 0.01 for that level of significance, which is that symbol pronounced alpha. There's a neat little memory aid there. If you need something to help you with, if the p is low, then you reject the null. So to continue, it says we need a number that can be used to determine if the p-value is small enough to reject the null hypothesis. This number is called the level of significance and is often denoted with the symbol alpha. If the p-value is less than the level of significance, we reject the null hypothesis. Conversely, if the p-value is greater than alpha, we fail to reject the null hypothesis. The level of significance, alpha, must be chosen prior to collecting the data. Go on to the next, talking about type 1 and type 2 errors, and this can get a little confusing. It says, if the null hypothesis is true, sometimes we will get a very large or very small sample mean. This will lead to a very extreme z-score strictly due to chance. In this case, we reject the null hypothesis even though it is true. It says whenever we reject a true null hypothesis, we say that a type 1 error has occurred or was committed. Assuming the null hypothesis is true, the level of significance alpha is the probability of getting a value of the test statistic that is extreme enough that the null hypothesis will be rejected. In other words, the level of significance alpha is the probability of committing a type 1 error. That will come useful in our quiz here. We choose a level of significance to be some small number so that the probability of committing a type 1 error is low. So we're always wanting to avoid that type 1 error. Assuming the null hypothesis is true, the level, reading this over again. The most common value of this alpha is 0.05, and then we also common choices, like I said before, are 0.1 and 0.01. The type 1 error is committed when we reject a true null hypothesis. Another problem that can arise is to fail to reject a false null hypothesis. So they got this little truth box that's got a decision, HO is true, HO is false. What I did is put, so your decision was to fail to reject the HO, or down below it is that you reject the HO, or the null hypothesis. If you fail to reject the null hypothesis and the HO is true, then it's just the correct decision. But like they said, when you reject a HO, when you fail to reject the HO and the HO is the HO is false. So it's false, but you failed to reject it saying that it was true. So you kind of did both. When you reject the HO, it's true, but you considered it to be false. And so that little graph will help you out. So if you failed to reject it and it was actually meant that the HO was true, that was the correct decision. But if it was actually false, but you now you can see how confusing this is. However, if it was false, but then you marked it true, then it's a type 2. And if you reject the HO and it was actually false, it was the correct decision. But if it was actually true and you rejected it, then it's a type 1 error. And it says below that, it says if the alpha value, the probability of committing a type 1 error is very small, then the probability of committing a type 2 error will be large. So if one of them, if you lower that value, the lower the value of the significance level alpha, as it goes down, say from 0.05 to 0.01, as that level of significance gets lower and lower, then the type error 1 goes down, but the other one goes up, and vice versa. As that number gets larger, then the type 2 error goes down and the type 1 error goes up. So we want to keep that value low enough because we're trying to prevent the type 1 error. Says conversely, if the alpha is always allowed to be very large, then the probability of committing a type 2 error will be very small, and we just talked about it. So it says here that 0.05 seems to strike a good balance. It says, however, the important thing is to choose it choose that level of significance before you collect your data. Another thing we add in here, on page 10, it says, how do you know, it's back to that sample mean, how do you know that the sample mean is normally distributed? And in our past test, basically the sample mean is normally distributed if the population mean is normally distributed. It doesn't matter on the number, the n value, the number of the sample size, sorry. And so there's two things. It says if the population is normally distributed, it's guaranteed, and if the sample size is large, and we already know that that's the central limit theorem that states as the sample size increases or gets larger, the sample size, the tendency of the data to be normally distributed increases with sample size. So about the only thing on those, the null hypothesis and alternative hypothesis, a really good little final summary on page 15 kind of gives you the remember things about the different things. And also finally on the errors, it gives a really good one. It says a type 1 error is committed when we reject a null hypothesis that is in reality true, and a type 2 error is committed when we fail to reject a null hypothesis that is in reality not true or false. And that the value of the level of significance is the probability of committing a type 1 error. So let me start screen sharing here. I'm going to bring up hopefully my iLearn page here. So let's bring up that. So that I can feel good about doing this lesson group meeting. This is why I'm posting this. I figured if Courtney posted hers by herself, and if I posted one that you guys could watch, that maybe that would be a justifiable thing. And since I just missed it, I wasn't. I was just about there, but it kind of didn't occur to work. So let's go through these. A hypothesis test consists of two hypotheses: the null hypothesis and the alternative hypothesis, and which one represents the status quo, or basically the one that's known to be true, and we know that to be the null hypothesis. It says here on the next number 4, which is a hypothesis that involves equality, and we know that anytime that we test a hypothesis, it's the null hypothesis that uses the equal sign or equality. Number 5, the p-value is the probability of obtaining a sample statistics at least as extreme as the one that was actually observed using the information to answer question 5. When computing this probability, which hypothesis do you assume to be true? And you always assume the null hypothesis to be true, and you use the alternative hypothesis to either fail to reject or reject it. And like we talked about before, they can be less than, greater than, or not equal to, and we can see that in this next question here. Suppose the null hypothesis is equal to 10. Which of the following represents the alternative hypothesis for a two-tailed test? And when we talk about two tails, it's the left and the right of that. And so in order to get that, this one right here is the only one that's two-tailed. So that is the answer. It's not equal to. says, which of the following represents the alternative hypothesis for a left-tailed test? And like I said earlier, if this is the population mean is here and that arrow points to the left, then hey, look, a left-tailed test. If it's a right-tailed, like on number 8, it points away and also is pointing to the right. So left, right-tailed, left-tailed, right-tailed, and two-tailed. Okay, the outcome of a hypothesis test is determined by comparing the p-value to the level of significance, or alpha. Use this information for question 910. Which relationship would result in failing to reject the null hypothesis? So when we say we're failing to reject the null hypothesis, our p-value is the determining factor. If that p-value is greater than that, then we fail to reject that. If it's less than that, then because this value here is we reject the null hypothesis. So the answer to this is that one right there. Which relationship would result in rejecting the null hypothesis? And like I said earlier, that's if our value is lower than the value that we set of 0.05 or whatever value it was, like gave us some ideas, 0.1 or 0.001. It says an insurance company is reviewing the current policy rates. When originally setting the rates, they believed that the average, so there's the belief that the average claim was this. So it was this. So we know that that says that the HO is going to be, or the null hypothesis is going to be equal to this. And it says they're concerned that the true mean is actually higher. So when it says actually higher, we look for this one right here. It's going to be greater. So that would be that one right there. And I thought I'd go back here and to page your text. On page 5, it says we only use greater than or less than if we have a belief in advance that the mean was less than or greater than. If we do not have a strong reason to believe the mean is either small or larger than the stated value before we collect our data, then we use that it's not equal to. So because they, in this question here, they said they believe it to be actually higher, that's the one we're going to go with. Which of the following would be appropriate for the null hypothesis? We always believe the null hypothesis to be true, and we know that it's always going to be equal to the value that they set, which is that $1,500. So the question is this equal to that? The insurance company randomly selects N40 claims and calculates the mean of 1650. The insurance company assumes the distribution of the sample mean is normal. Is this a good assumption? And we do, because remember if the sample mean is assumed to be normally distributed, then automatically it's going to be normally distributed. So let's see. And oh no, sorry here. When a sample mean is normal, it's this number right here, and is greater than 30. And so what theorem and law justifies this? And from our previous lesson, it was the central limit theorem, which is following is a test statistic. And we talked about that on earlier And that test statistic is found on page 6, and it's the Z. The Z is the test statistic. Okay. It says we will use the significance of the level of significance is 0.05. So that's the value we're going to set if our value that we get, or our Z, the p-value is going to be lower than that or above that. That's what we're going to use to determine if we're going to fail to reject or reject the null hypothesis. So I went through and calculated this using the Z equals the sample mean minus the population mean divided by the standard deviation divided by the square root of n. So I plugged in 144 minus this up here, that's 150 divided by 40 divided by the square root of 36, and I come up with that my z-score was this. So then you go over to applet and you type in your new z-score. Let me go back there really quick. Negative 0.900. Okay. I'm going to actually draw this, grab this and bring this in. This helps me because once it's too far out. So that I'm going to type in here 0.900. Okay, and if we look at our thing, it says here's was our thing. Our test was that it was going to be less than this. So then what we do is we shade, because it's going to be a left-sided tail because of where the arrow points. And we come to this template and we take the shade off of there. And so here's the probability of 0.841. Okay, what inference would you make about the null hypothesis for this problem? Well, our level of significance was this, and this is what the probability value of that occurring. And so because it is still higher than that, we can't reject it. We have to fail to reject it. The next one. Here we go. There's two types of errors that can be made when performing a hypothesis test. Which one involves rejecting the null hypothesis when the null hypothesis is true? So if you reject that null hypothesis, but in reality it's actually true, so you're saying that it's false, but it's actually true, you committed what they call a type 1 error. A researcher decides that instead of using this level of significance of this, he will use this. So when you lower this value or raise this value, it's basically on your, like we talked about this on page number 8, it says towards underneath the truth box, it says if that value or the level of significance value, the probability of committing a type 1 error is very small, and the probability of committing a type 2 error will be large. So as this number goes smaller, it kind of like goes up and down. The type 1 decreases, type 2 goes up, and alternate, if this value goes up, then type 1 increases and type 2 decreases. So in this one right here, because they made it smaller, it will increase a type 2 because it's decreasing the type 1. Okay, if the level of significance is 0.05. Compute the probability of committing a type 1 error. Well, here it is. Your level of significance is that probability. So whatever this value is, it's that probability of committing that type of error. So this answer is 0.05. So hope that works for somebody. I know it's probably at this time either too late. It's getting about 10:57. Took me a while to get this going. Hope this is some value. I felt like I should post this due to the fact that I just missed the group meeting. Didn't mean to. I always have good intentions to be there. I have the time set aside for it. My internet this time just got me, so I was able to get it back up. Figured I could participate by letting you guys hear what I have to interject into this message. So we'll meet again on next week, and good luck. Hopefully the test went well for you. You guys all have yourself a good evening, and thanks for watching.